a snowmobile is used to pull two sleds across the ice. Okay. The mass of the snowmobile and the rider is what? Is 320 kilograms. And according to our sig fig situation, this is two sig figs because the zero at the end does not count. The mass of the first sled behind the snowmobile is 120 kilograms. And the mass of the second sled behind the first sled is 140. The ground exerts a force of 1,500 newtons forward on the snowmobile. So that's basically the what? That's the actual, that's the actual like forward motion or forward force on the snowmobile. The coefficient of kinetic friction for the sleds on ice is 0.15. Assume that there are no other frictional force acting on the snowmobile. Calculate the acceleration of the snowmobile and sleds, like everything. Okay, lots of things, right? Okay, let's sketch a system diagram first. So here's our system diagram. So here's the ground. Okay, how many objects should we sketch? Like what objects are mentioned in the problem? Snowmobile. So snowmobile. I'm just going to sketch the snowmobile like this. Okay, so this is the snowmobile. Okay, what's behind it? One sled. Oops, sorry. And then there's another what? There's another sled. Okay. This is no. So sled, and they're connected with what? With tension here and tension here. Okay, relax. Okay. Oh my God, what am I sketching at this? Okay. This has a mass of how much? 320 kilograms. Okay. What's the mass of the first sled? 120. How about the other one? 140. Okay. Is the whole system moving together? Are they connected by strings or springs? We always assume they're connected with what? No. Remember springs? Springs means what? I'm going to move for a while before Omar moves, right? So that means what? It's always strings or cables. So that means the whole system is moving together. So that means they're all under one motion direction this way. No, they're being pulled by this snowmobile. This is the one with the engine. Oh, it's pushing on the ice, so the ice is pushing back. Basically, the walking principle. Okay, the walking principle. So motion is always going to be given what sign? Positive, which means pretty much this is negative for sure. Okay, let's yes. So think about it this way: the engine force is the engine force is 1,500 newtons forward. Because remember, the engine basically what the engine makes the tire. Yeah. No. Okay. How does the engine make something move forward? The engine rotates the tires. The tires push back on the ground. So the ground push what? That's basic. Again, it's the walking principle. My engine is my leg muscles. They push back on the earth. The earth pushes forward on me. Okay. By the way, just so you know, I will never tell it to you like that. I will always tell you there's a what? There's a forward force of 1,500 newtons on the sled. Sorry, on the snowmobile. Done. I will tell you exactly how to actually put. I'm not gonna tell you, oh, the ground is pushing. I'm gonna tell you there's a forward push. Okay. Let's do the forces on the what, everyone? Let's do the forces on the snowmobile. What's force number one? Okay, so, and let's number them now. Let's call the snowmobile what? 1, 2, 3. So this is FG1, which means this is what? FN1. Is there forward motion? Sorry, is there a forward force on the snowmobile? Yes, there is. So we're going to call it just what? F applied. You can call it F engine, but F applied is good enough. Because there is a forward force on the snowmobile, making it go forward and pull everything behind it. Which is the engine, yes. As the force applied, yes. Is there friction on the snowmobile? Read the question. Is there friction on the snowmobile? No, they're saying what? Assume there are no frictional forces act on the what? On the snowmobile. But is there tension under it? Yes. In which rope? In this rope right here. So you go and you put T, and we're going to call it T what? T1. Are there any other forces on the snowmobile? No more, no other tensions, no gravity, no other gravity, no other normal, no other applied, and no friction. Okay, let's go to the first sled. What forces are on the first sled? Gravity. So we're going to call that FG2. FG2. Which means there's a what? Normal force 2. What pulls it forward? Tension, which is also what? Which is also what? T1, but on the other side. Remember, a single piece of rope has the same tension all inside of it. So you're going to have to put T1 here. Oh, because T2 will be in the other rope. Every rope has one subscript for tension. The entire rope, sorry, every single piece has its own tension. So T1 this way, T1 this way, T2 this way, T2 this way. Okay. Is there friction on this one? Is there friction on the first sled? There's the coefficient of kinetic friction for the sled. So this one has what? Has Fs or Fk because it's already in motion. So I don't have space here. I hope you might like if you sketch the, I have no idea why I sketched the slide so close. So I'm just gonna go what? I'm gonna go this way. I'm gonna go F, K, 1. Okay, everyone? There should be a force going this way. I just don't have space. FK1. Oh, can you put it actually below the ground? Can you actually, okay, if you are a fan of putting friction where it really is, you are more than welcome to put it right here. Actually, let me do so if I can erase. I'm not sure if the eraser works. The eraser doesn't work. Okay. So I'm just gonna take it out. Is there another tension on the first sled? Because it's connected from the back, right? What do you call that tension? T, T2. So there is T2. Are there any other forces on the first sled? Or are we done? First sled, are we done with all the forces on it? Yes, we are. Let's go to the last sled. What's the first force on the last sled? Gravity, so FG3. FN3. What's pulling the second sled forward? Tension, but which one? T1 or T2? Directly T2. So this should be T. Is there friction on it? What do you call that? FK? FK2, because there's already FK1 on, oops, sorry. Fk what? 2. Are there any other forces on the last sled? No, no more applied. No applied. Applied is all the way at the front, and that's it. How many objects do we have here? 3. So technically, we have 3 FBDs, right? 3 FBDs on the same system diagram. So now we're gonna go to the what? To the. So okay, question. What does the question actually want? Calculate the what? Which one? Which one is the most complicated or the busiest FBD? The second sled, first sled, or the snowmobile? No, no. Like which one has the most number of forces on it? The first sled has 1, 2, 3, 4. This one has 1, 2, 3, 4, 5. This one has 1, 2, 3, 4. Right? Okay. Let's just think about this for a second. Everyone, pencils down. Let's look at the snowmobile. What forces on it can we calculate? Or what forces on it do we know? Do we know the Fg on the snowmobile? What's the equation for Fg on Earth? 9.8 is only the G part. You still need to multiply it by your what? By your own mass. Do we have the mass of that snowmobile? Perfect. So if you have the mass and you know the planet, check mark on this. Do we know the applied force on it? Do we know the normal force on it? We do indirectly, because for every single piece, this one is equal to what? Make sense? Because no object is moving up. Or okay, so we have this one. We have this one. We have this one. Do we have this one? No, we don't. Okay, hold on. How about this one? Can we calculate Fg2? Can we calculate Fn2? Do we know T1? Do we know T2? Can we calculate Fk1? Think. What's the formula for Fk or Fs? They're really the same structure. Mu k, which we have, times what? Fn. Remember, in every friction problem, get the y-axis done first. But we still have how many unknowns? 2 unknowns. How about this one? Do we know this? Do we know this? Do we know this? Right now, can we find it? Do we know this? Okay. Question for you. Can you imagine how the system would like if you took out the ropes and just like molded the whole thing together? Would it still be moving exactly as what? As the exact same as the exact same, oh my god, as the exact same unit? Yes, it would. Tension is always gonna what? Cancel itself out when you put all the equations in. Let me show you what I mean. So let's go to the next slide, everyone. The blank slide. Okay, let me see how much space you have. Okay. Okay, everyone. We're going to do 4 levels. So we're going, actually, okay. This is what I have in mind. Where's my, not my day. I'm sorry, I have no idea what's going on today. What the? Okay, I want you to divide this into 3. Not the whole thing. Just halfway. Why 3? Because we have what? 3 objects or 3 FBDs. Okay. For every object, listen up. We're going to take a shortcut here. For every object, is there an up or a down motion? Is there an up or a down motion? No, there isn't, which means for every object, Fn is equal to what? Fn is equal to Fg. So that's the first thing we got to write. Fn1. I know we should say what first? Y-axis, no motion, means what? F net equals 0 means what? Fn1 equals Fg1. Yeah. We need to because we're going to use it. Okay, listen up. X-axis for the snowmobile. How many forces on the x-axis for the snowmobile? I'm going to go back to the slide. How many? One pointing what? And one pointing. So when you do the F net, are they both going to add, both going to subtract, or one positive, one minus? One of them is going to get a positive sign, and one of them is going to get what? Because one of them is pointing with motion, and one of them is pointing. All right. So, say again. They have applied this way and the tension that way. Yes. So, everyone. Oh, is it accelerating on the x-axis? Well, what's the question asking for? Calculate the acceleration. So that means what? On the x-axis is Newton's second law. So go ahead. F net equals m1, m1g or m1a? Yes, Newton's law is ma, not mg. Ma. And what is it? Plus force applied, subtract tension 1 or tension 2? Tension 1 equals what? Equals what? M1A. Yes, sir. Yes, absolutely. All right, let's do the second one in a different color. Yes? It's gotta be, thank you. It's gotta be F net on the X, which is mostly what we're gonna be interested in. Good job. Yes. Okay, next one. Fn2 equals what? Fg, which is equal to what? Okay. How many horizontal forces are on the second or the first sled? Sorry. Or the second object, I say. I'll go to the slide. How many? 3. How many are pointing? How many are pointing forward? Which one? Tension 1. How many are pointing backward? Tension 2 and both of these get what sign? There you go. Whatever is pointing with motion gets a positive sign. Whatever is pointing against motion gets a negative sign. All right. So F net. Technically, we have to say F net what? F net. No. F net on the x-axis. But don't worry. Every F net we're gonna almost do in this course is gonna be on the x-axis. F net equals M2A. All right. We said which force is gonna get a positive? Plus T1 subtract T2. Let's say, yeah, let's go with T2 first. Subtract FK1. You got it. Equals what? M2A. Which one of those three forces can you break down into even more? Like, do you have an equation for? Sorry. FK1. So this becomes T1 minus T2 minus. What's the equation for FK? Two things multiply. UK times Fn. And what's Fn? We got it on the first line, M2G. So I'm going to jump straight to what? Mu K M2G equals what? M2A. Because that's the equation for what? That's the equation for FK. Yes. One second. Okay, good. Okay. How many people agree with this step? How many people agree that this is mu k Fn? But what's Fn? That's why I'm always saying, write all the equations you need on the side, because you know you're going to have to what? Reuse them again. How many FBDs do we have left? One. Let's do a different color. Let's do blue. All right. What do I still start saying? Fn3, Fg3, which is equal to what? M3G. Okay. How many horizontal forces are on the back sled? How many? Two. What's pulling it forward? Tension 2. What's pulling it back? Or sorry, what's not pulling? What's resisting it backward? Fk2. So F net equals M3A, which means what? Plus what? T2. Subtract Fk2 equals M3A. Which force can you break down more equation-wise? Fk only, because the other one is just a symbol. So T2 minus mu. I don't know how to take this up. Okay, T2 minus mu k what? M3G equals. No. Okay, everyone. How many people got this done so far? How many people still have almost half the slide left? Okay. Can you remind me what? Okay, remember substitution and elimination for grade 10, the one we used yesterday? Can you still use elimination with 3 equations? Yes, you can. Check this out. What's the sign of T1 here? What's the sign of T1 here? If you pile them on top of each other, what do they do to each other? What's the sign of T2 here? What's the sign of T2 here? Is that always going to happen in any tension problem? 100% of the time. Why? Because every rope has tension in how many directions? 2. But are they together or opposite? Always opposite when you combine what? Different FBDs. And by the way, this is going to lead us to today's pulleys lesson. So what am I going to do now? I'm going to write this equation. So let's actually do it in a neutral color, so black. So F applied minus what? Equals. What's going to be under it? Plus T1. I'm just putting the plus to confirm to you that's going to cancel itself out. Minus T2 minus mu k M2G equals what? M2A. What's my third equation? Plus T2 subtract my mu k, sorry, M3G equals what? M3A. I'm just going to hide this. What's going to happen here? Which 4 things are going to cancel? 4 things. The 2 T1s and the 2 what? And the 2 T2s. So I'm going to do it in. This one is going to cancel itself. And this one is going to cancel itself. So what else is going to survive? Everything else. So what's going to be the equation here? What goes down? Everything else. F applied Those do it in black. F applied. Do I what? Wait a minute. I want to hear this. Do I square what? The what? What coefficient? Why would I square it? It's not times. Everyone, are we timesing or multiplying these equations or just adding them up? Adding. So that means what? Minus cancels a plus. Minus cancels a plus. This is going to go down with a plus. This is going to go down with a minus. This is going to go down with a minus. And on the other side, all of them will go down as what? As positive. Do you see me? You just literally bring them down as they are. So minus mu k m2g minus mu k question. What's a common factor here? What is this equal to? Do you care about the A or the numbers? Numbers. So literally, we just have to out now. You can think of it as what? The full mass of the system times A. Do you see what I mean? The full mass, because the whole system is moving together at one acceleration. So feel free to write this. M1, welcome to factoring. Can we solve this now? Do we have everything we know except for the A? Do we know the applied force? Do we know the applied force? How much? 1500 newtons or just 1500? Do we know the two mu k's? Do we know the two masses? Do we know the G? You can literally plug in now. Yes. I did. I added M1A plus M2A plus M3A. But because I know that this one could be factored out, I factored it out, and I just remained with what those three together. Oh, how many people remember factoring? What's common factoring? You need to look at what one thing that appears in everything and what? Take it out. How many people? Okay. How many people remember what's the opposite of factoring? Starts with E. Expanding. Got it? How do you expand? You multiply this inside, right? What's M1 times A? M1A. Do you see what I mean? Factor just to make your life easier, not to solve, just to make your life easier. Yep. Okay, so I'm just gonna leave the rest as an exercise for you, but you should get the exact same answer that the question has, which is how much? Apparently, the acceleration of the entire system speeding up together is 1.9 meters per second squared, obviously forward, which you never have to tell me. Okay? So listen up. Question, everyone. What's the take-home message? Listen up, isn't? What's the take-home message from today's lesson about any problem with tension forces? If you combine equations for FPDs, what are the tensions definitely going to do to each other? They have got to cancel out. If they do not cancel out, that means what? You made a what? You probably made a mistake that's so simple. What? You probably have two T1s with the same what? With the same sign. Do you see what I mean? That's why elimination is always going to work in what? In tension problems, because tension is always going to what? Cancel itself out. It's still there, but it's going to cancel itself out. So my question to you is now, listen up. How would you calculate the tension in the two ropes after you calculated acceleration? You have how many equations you can use? 3. But one of them has how many tensions in it? Let's steer away from that one. Can I use this one to calculate T2 once I know A? Yeah, because I can plug this in, this, and the 1.9. And I can solve for what? T2. Can I use this one to solve for T1? probably much easier because I can plug in 1500. M1 is, I think, 320 times 1.9, and move this one here and move this one here. Do you see what I mean? You still need the tensions to manufacture the system, but you still need to find what first? You need to find acceleration of the system first. Yes. Say again? See, that's the thing about a spring. At the beginning, I was moving, you were not moving. But then what happened? There was enough force built up in the spring that it turned into a string. Do you see what I mean? And then we're gonna move together until I what? But you're not gonna stop, right? Until you compress the spring enough to say stop. Do you see what I mean? Springs are always tricky, and that's why you never assume that what? That they are the connection mechanism. Unless you do mechanical engineering and that kind of stuff. Good. Or car shock absorption. Okay, let's do one more problem because I want to get to the police. So a lawnmower accelerates, sorry, a lawnmower of what mass? 15 kilograms. What does it start with? Come on. What does it start with? What speed? No. What speed? From rest. Okay, that's a kinematic thing. Fine. To what speed? And what, sorry, during what time? You've got VI, you've got VF, you've got time. Even if you didn't know anything about forces and you just finished kinematics, what can you calculate? Perfect. Okay. The coefficient of kinetic friction is 0.25. How much is the applied force on the what? On the lawnmower, on the object. Okay. What is the most important object in this problem? Well, let's sketch a box on the floor. All right. Floor, lawnmower. What's the first force on the lawnmower? Always. What's the first force? Gravity. Go ahead. Fg. It's on the ground. So definitely what force is pushing, or sorry, supporting it up? Normal. You got it. They're always come in pairs. Is there a horizontal applied force on it? Yes. It's saying that it's being explicitly pushed. Even the question is asking, calculate the applied force. So we're going to say that the applied force, I'm going to say it's being pushed this way. Again, you could have pushed it the other way because there's no direction indicated. Is there friction in this problem? What kind of friction? It's in motion. It has to be kinetic. Which way is it? With applied or against? I'm going to even sketch it low here to give it a feel of what? Of the floor giving off the friction. Why is it? Because it's in motion. Remember, kinetic friction is what slows things down. Static friction is what prevents me from moving something static. What's the motion direction here? Left or right? What's the motion direction here? Motion direction always has to go with applied force. By the way, could motion direction ever go with friction? No. The best that friction could do is what? Slow you down, not push you backward. It's important to understand this. Even though it's a force pointing that way, it doesn't physically what? Push you that way. It steals from the applied force that way. Okay? Always think of it this way. You're losing energy. So let's go with motion like this, everyone. Motion. And what motion direction, what the sign do we get? Positive here, negative here. Okay. Does this problem involve friction? Whenever you involve friction, which axis do you always start with? You get it out of the way. The X or the Y? The Y, because you know you're going to need which force on the Y? The normal force. Perfect. By the way, this will never, this idea will never fail. Grade 11, grade 12, first year. If you have friction, do the Y first. You're going to have to recycle that information. Okay. So let's start with the what? With the calculation. So we're just going to say y-axis. I'm just going to say y-axis. Fn equals what? Fg which in turn equals, check, done. That's it for the y-axis. How many forces are on the x-axis? Are they pointing together or opposite? So that means one of them is positive and one of them is, so let's say x-axis, second law, which is F net equals what? F net equals M. Okay. Literally, because they said in the question what? Accelerates. Whenever you hear the two magic words, accelerate or decelerate, you go with the second law. Which force is going to get the positive sign? Applied force or friction? Friction never gets positive. It always gets the what? Because it's always going to go with, sorry, against motion. So positive F applied minus Fk equals still what? By the way, this is the beautiful thing about F net equals Ma. This side will never change. It's this one you need to keep breaking down. What's the equation for Fk? Come on. Mu k Fn. So this will become F applied minus mu k times the normal force equals Ma. What? 100%. I just wanted to at least show you one where I don't skip a step. How can you simplify the math before actually plugging in? Yes, Mo? Oops, sorry. Oh, okay, before you answer, go ahead. Why do you? Because I have no idea what the Fn itself. You got it. Can someone tell me how to simplify the math here? We kind of did it yesterday. Say again. Cancel the what? Oh, sorry. One second, one second. Okay, everyone, just hold on. Don't do any more. What was your question? There's no such thing. Seriously. You mean this one and this one? Oh, I am just step by step breaking it down. In the equation we just did before, I skipped from here to what? To here. I don't want to do that every single time. How many people disagree with what I just did here? I have to admit, I played reverse psychology on it. I did ask you a tricky question. I said, how can I simplify my math? It was something we did yesterday. Is M common to every single thing in the equation? There you go. Now you know why math teachers hate the word what? Cancel or cross out. Because everyone does it once they see what? Two copies of the same thing. Is two copies enough? How many copies do you need to have? In this case, but in general, how many? You need a copy in every single term. What if there was an M here? Could I cancel then? Can you ever cancel if it's not fully common? It's called common factoring for a reason. That's why math teachers, trust me, you go to Mr. Fonseca or Mr. Shivers, they will never say what? Cancel out or even cross out. They will always say what? Factored out or divided out, because they know that people just what? Cross out without knowing why it does or it doesn't work. So can we cross out here? Sorry, we can't. So that means what? It's okay. We'll just plug in the numbers. So undo, undo, undo. What numbers do we have given to us here? Do we know the applied force? No, we want to find it. Do we know the mu k? Check. Do we know the mass? G. Always. Do we know this? Can we find it? Great. Everyone, let's do a side calculation real quick. Can someone tell me what's the kinematic equation for acceleration? Or what's the definition of acceleration? Vf subtract Vi divide by delta t. All right, let's do this. Yes, start it. Go ahead. Uh-huh. From rest. What does that mean? What's the initial speed? 0. Fill it in. Oh, no, no. Okay. Think about it this way. You kept pushing, pushing, pushing until it started moving from rest. And then kinetic friction took over. You see what I mean? Yeah. What was the final speed it got to? 1.5. Is everything in meters per second? All right. 1.5. How much time did it take? 1.2. I believe that is. Oh, 1.2 for the VF. Sorry. So how much is for the time? 2 seconds. Okay. Got it. So where does this 0.6 go in the equation? So let's do this real quick. So we'll have a break. We'll have a break. F applied equals, sorry, minus. Oh, how many people are, I just want to show of hand here. How many people would rather arrange the equation first and then plug in? How many people would plug in and then rearrange? Doesn't matter. You should get the same answer either way. So minus what? I believe it was 0.25. What was the mass? 15. 9.8 equals what? Done. So it's F applied. Subtract. I have no idea what this is. Someone need to help me with that. Uh-huh. How many people got this number? Actually, it does make sense. Equals what? 15 times 6. That's easy. That's a solid 9. So what do I do? Which number moves to the other side? The negative 36.7. So our applied force is 46 Newton.